So I got this rocket ship that's blasting off from Earth, and I want to think about how much work is done. As the rocket leaves Earth, so they're going to start off here. Keep in mind that when they start off, this rocket, obviously not drawn to scale, and most likely designed by one of the billionaires of the world to save humanity, is going to blast off from Earth. Now, as they blast off from Earth, I want to point out that the force due to gravity acting on this rocket is going to drop, actually as an inverse square law, right? And so if I want to figure out how much work is done on this rocket, I can't just say work is equal to force times displacement, because the amount of force that you're working against changes as a function of 1 over r squared. And so I really shouldn't be doing that. What I really should be doing is talking about gravitational potential energy. And gravitational potential energy is negative g mass of the body that you're escaping, the mass of the body that's leaving, divided by r. And that's a formula that we've looked at before. And yet there's definitely a negative sign there. So this curve here that I've just drawn is what the shape of the force as a function of radius would look like, an inverse square law. This 1 over r relationship would look something more like this from the negative axis. So if this was like, this red curve was the negative gravitational potential energy as you get further and further and further away. Notice that the r value getting smaller and smaller, getting larger and larger and larger would mean that the Eg value is negative but less negative. That's my red curve, okay? The red curve would be like a function of this Eg value. Like if this was the negative axis and this was the positive axis for a graph, Eg is negative the whole time, but less and less and less negative. And so when people talk about climbing out of a gravity well, this is the energy well that you're climbing out of when you're trying to blast off from a planet. And people even talk about things like limits. And in math class, you might talk about the limits where a variable like radius approaches infinity. How many people have seen that kind of notation? Sometimes they'll write it as like the limit as r goes to infinity. Is that the notation you guys like? For the function Eg as a function of r. Can you imagine that being something that could show up in math class, right? This is functional notation. But this is grade 12 physics, so I'm trying not to blur the lines too much, but it's hard not to talk about it. So we could talk about, hey, what happens in these extremes? Well, in the limit where Eg goes to infinity, Eg negative g me mass of the rocket divided by r. In the limit where r goes to infinity, what does Eg become? Zero. In fact, I could say negative 0, but it's 0, right? And then in the limit where r goes to 0, that is when you're like approaching the center of a planet, I guess. Eg, I don't know what that, I will use that functional notation. Eg of r equals what? If r becomes 0, what would the Eg value be? Yeah? Negative infinity. Now, do you ever get to the center of the planet? No. But the Eg value gets quite large in magnitude and negative. Okay, so that idea of an energy well that you're trying to get out of. By the way, this idea of the limits as r approaches infinity and 0 and infinity, also is something that could come up in chemistry if you're talking about electrons escaping an electric potential well. You talk about ionization. To ionize an atom, you would talk about the ionization being an electron escaping from an electric potential well. That's a way to talk about this kind of thing, right? So that binding energy that we talk about with electrons in chemistry, maybe there's some overlap here with how we would talk about stuff. And so I kind of love that. There's this nice overlap. Oh, look at that. All in one spot. I talked about chemistry, calculus, and physics. And I think that that really speaks to the fact that like these different areas are not siloed, separate concepts, right? They really are like interwoven with one another. And I think that that's exciting. I love that these things overlap with one another. Which brings me to soccer balls. On a different note, When you kick a soccer ball, like bringing it back down to earth again, when you kick a soccer ball, remember that this soccer ball might start out at 20 meters per second. When it gets up to the top, let's just call this V2, is the speed 0? No. The speed is minimized. What I can say is that Vy is equal to 0 meters per second, if I want to think about kinematics and components. But V2y, V2x is equal to, well, let's just say not 0 meters per second. We know from kinematics that V2x and whatever V1x is, V1x would be equal to V1 times cosine of theta, and V2x would be equal to the magnitude of V1x in the absence of drag. In other words, the kinetic energy doesn't disappear, the kinetic energy is minimized. And it still follows the rules of kinematics. So that's something that I want to throw out there because you might encounter a homework problem like that. And if I don't mention this, there's always going to be a subset of people that say, oh, at the top the velocity is 0. Oh no, kinematics didn't disappear. It's still a thing, okay? So I just want to make sure that we're all aware of that. Now when it gets back down to this point right here, we could say, oh, wait a minute. I don't really need to talk about x and y components. I actually didn't even really need to talk about x and y components here. What I could talk about up here is I could say, well, Eg total, in the absence of drag, Eg total A, or Eg total 1, I guess we call them 1, is equal to Eg, oh my gosh, I got too many indices there. E total 1 is equal to E total 2, which is equal to Eg2 plus Ek2. And if I didn't want to think about V1x being equal to V2x, I could say, hey, at the top, Ek2 is equal to 0, but if I do know the height, I can calculate Eg2. If there's no drag, then I know that E total 1 and E total 2 are the same, and I could calculate for Ek2, recognizing that whatever speed I get out of that Ek2 would be the V1x value. Okay, so I just wanted to tie that back together. And then when I get to this point here, if I wanted to find V3, I could use the exact same logic. The only thing is, whatever V value I get isn't V1x anymore. It's just the instantaneous tangential speed to the parabola as it gets to that point on the curve. Does that make sense? Now people say, well, could I deconstruct that a little bit? Well, sure, yeah. If I know what the speed is there for conservation energy rules, then that V1x would still be its x component. And I could, if I wanted to, calculate what the Vy component is, right? Because whatever this Vx is, it's equal to the V1x value. This V3 value here is equal to the speed that I would get out of a conservation of energy argument. And I could use Pythagorean theorem to get V3y. Okay, so again, just stitching ideas together, right? There, what is this? I was with my daughter at the park. Oh, I'll let you look at that later. Something about pushing my daughter all the way around on a swing. Let's go back to this, though, on the idea of swings. This is a pendulum. This is one where I want to talk about the geometry of pendulums, because if I don't talk about the geometry of pendulums, people get lost. I've got a pendulum that's a length 10 meters. I'm not even sure if I want to do the math on this. I just want to talk about the ideas. I'm going to label that length cursive letter L. And I want to say that a pendulum starts off at its highest position, I'll call it position 1, and it swings down to its lowest position, I'll call it position 2. At position 1, I'll just choose the bottom of the ball as my reference. At position 2, I'll choose the bottom of the ball as my reference. Remember, with conservation of energy, if this ball swings down, we're talking about a change of height. And so the change of height between position 1 and position 2, we could talk about it as h. Specifically, if I call position 2 height of 0, I would say that that distance, that change of height, would be height 1. Now the way I've drawn this, the pendulum's at the lowest position it would swing to. If I wanted to talk about conservation of energy and figure out how fast that pendulum was going at its lowest point, that would be its maximum speed. which makes sense. We'd want to do that. It could be a wrecking ball. It could be a clock pendulum. I don't know what it is that we're dealing with here. If it was a wrecking ball, we'd want to know what kind of speed the wrecking ball could get up to before smashing down a wall or something. But that horizontal line and the vertical line create a right angled triangle. So this is my height 0. That upper line is my height 1. Keep in mind that whatever the length is for this rope, the length, I'll draw it in red, goes all the way. Now maybe I'll extend this length. Look, length is the whole length. That length is still this length. It's still the L value, even when it swings down. This is 40 degrees. If it swings by 40 degrees, this value here is not the length. This value here, I'm going to give, because I lack good language for this one, I'm just going to call it Y. And what I notice is that because there's a right angle triangle here, and I know the hypotenuse is 10 meters, I'd like to figure out Y. And if I figure out Y, well, let's just write this down. It seems to me that length is equal to height 1 plus Y. In other words, height 1 is equal to length minus Y. I'm going to put a box around that. I'm going to call it equation 1. It also seems to me, by looking at this right angled triangle, that cosine of theta, that 40 degrees, cosine of theta is equal to adjacent over hypotenuse, so Y divided by the hypotenuse L. And again, I'd like to rearrange this thing, and I think I'll get Y all by itself. I say Y is equal to L cos theta. I'm going to put a box around that, and I'm going to call it equation 2. And I'd like to sub 2 into 1. Okay, and if I sub 2 into 1, then I end up saying, okay, well that means that the height 1, is equal to L minus L cos theta. That's nice because it finds the height of my initial position in terms of the length of the pendulum and the angle to which it's originally swung out to. That's a nice, cute little way of finding the height. Now, once I do that, for this particular object, I could say, hey, look, EG1 plus EK1 equals EG2 plus EK2. If I've already defined position 2 as the 0 height, EG2 is 0. If I start my pendulum from rest, or if I start it from motion, I can deal with this, but I'm just going to say if I start it from rest, EK1 is also 0. So if I do a little bit of a rearranging here, I can take this H1 and plug it into my EG1 expression, and I can go from there based on the information that I have here, and I can calculate what the kinetic energy is going to be at the bottom of the swing. And what I'm going to challenge you folks to do, I want you to try it. See if you can do it. If you're able to expand this out, mass times acceleration due to gravity times height 1 equals 1/2 mv2 squared. Let me just point this out. What happens to the m's? I actually do know that this wrecking ball is 80 kilograms, but I didn't need to know it, right? Notice that the masses disappear. And I'll let you take this to completion, check your work, but if you do everything right, you should get a V2 value, a maximum swing speed for this wrecking ball of 6.775 meters per second, or rounded off, about 6.8 meters per second. Well, I guess it's, I don't know what's after this 5, but 6.78 anyway. Sorry, I didn't write that down. All right, so give it a try. Make sure that you can do it. Just build that confidence.